one. Hi, welcome to Theoretically Podcasting. I'm some guy on the internet, and today I'm joined by Professors Suvrat Raju from ICTS in Bangalore and Geoff Pennington from UC Berkeley. Welcome to you both.
Thank you. Hey, good to be here.
And I thought I'd title this discussion Islands to be Discovered. So islands in this context, well, we'll hear a more technical definition soon, but it's basically holography's way of making sense of black hole evaporation, to put it in very few words. But let's actually begin with how each of you would define what islands are, so that we can then proceed to points of agreement, disagreement, and so on. So we can start in the middle. Doesn't have to be it doesn't have to be from the very beginning. So for whatever reason, Zoom has rendered Suvrat as a large screen. So let's start with you.
I see. In fact, this is probably a question that Geoff should answer, because I would think of islands as just as an entanglement wedge that's disconnected from the asymptotic region of
space. I think that's a perfectly good definition. We could maybe get into what an entanglement wedge means and so on, but I think for now, at a very high level, I would just say it's some region of space-time that is normally inside the interior of the black hole. Sometimes it might stick a little bit outside the black hole, but it's some compact region of space-time not connected to any asymptotic boundary, as Suvrat said. That in some sense is holographically dual to some radiation that semi-classically seems to be space-like separated from it. So we expect that black holes radiate, and then we expect that well, we can maybe get into this later, but the traditional expectation is that that radiation eventually encodes information that fell into the black hole. And islands seem to be the way that semi-classical gravity knows that should happen. And we can get into why that's true and how that's true and so on later. But it seems to be some region of space-time that, even though in a semi-classically description, it's some distinct set of degrees of freedom from the radiation, then great. So we have a nice little diagram here. So even though you have some semi-classical radiation that seems to be just space-like separated, so independent from the island, then secretly any information that is in the island is non-perturbtively encoded in this radiation.
You're muted.
Great. Yeah. Oh, sorry about that. So since we touched on this, let's also maybe have a brief description of what an entanglement wedge is, just so we're clear on terms before we go into.
Yeah, I think I'd sort of want to avoid talking too much about that beyond what I said, because it gets into ADS-CFT, and well, islands came out of ADS-CFT. I don't think they fundamentally have that much to do with ADS-CFT. They obviously can be realized in that. Perhaps, yeah.
Maybe
one way to motivate about it is to talk about where they come from. But yeah, let me say how I would describe how you end up considering an island. So okay. We have some black hole.
Yeah, but just before that, sorry, could I attempt a short answer to Vasu's question before you say how you get the island? Yeah, I think in this figure that's shown, I think the proposal is, even for those who are non-experts, that if you look at the degrees of freedom in what's called sigma island, those are somehow redundant with the degrees of freedom in what is called sigma rad. So in some sense, if you think of a quantum mechanical observable, some observation you can make in sigma island. There's another description of the same observable. It's really the same observable, which exists in sigma rad, and that's the proposal. So yeah, entanglement wedge is roughly about redundancy of degrees of freedom. So there's some degree of freedom that has some description somewhere in the bulk, and there's that same observable can be represented somewhere else. In this case, it's sigma island and sigma rad.
Cool. That works, I guess. but Geoff, you're gonna tell us how you get to the islands.
Yeah, good. So how do these things arise? So sort of the easiest way to think about them. So the other property that an island tells you, in addition to where information is it also tells you about entropy. So entropy is some measure of how noisy some system is, say some quantum system. And if we have a black hole that is radiating photons, then we can calculate what entropy, how entropic those photons are. There's a standard calculation that goes back to Stephen Hawking that says if we collect a few photons of Hawking radiation, turns out that entropy it follows what's called a thermal entropy formula. And basically, each photon that comes out carries roughly 1 bit of entropy. And the more photons you get, the entropy grows just linearly with the number of photons. So roughly you have n bits of radiation. They will have an entropy that is equal to n. And that's related to those photons not seeming to carry any information, because having an entropy of n means you're just in a totally random state. The probability distribution over all states they can be in is just sort of maximally mixed. Each state is equally likely. But on general grounds of how quantum systems work, we expect that at a more fundamental level, then sort of information is always there. If we looked at all the degrees of freedom of the system, then at any given time, there wouldn't be any entropy. The system would be in a well-defined state. We might not know what it is, but that state exists. And there's general laws of quantum mechanics that say if you look at sort of more than half of the relevant degrees of freedom in the system, excited degrees of freedom, then they can no longer be in a maximally entropic state. They can no longer just be totally random distribution if the overall state of the entire system is going to be well defined, and if you're not going to have lost information from your global state. So that tells us that at some point, roughly halfway through the evaporation, when the radiation degrees of freedom, these photons become more than half of the relevant degrees of freedom of the system. And there's possibly words I'm saying here that Suvrat will disagree with, so we should get into that later. I should say this is the standard story. This is not my story. This is the sort of canonical story that goes back a few decades. But you know, there are complaints that can be made about it, of course, as with anything. At some point, the entropy starts going down, and the state of these radiation modes stop being pure. And so you can ask, how can we tell whether that's happening? Say we, as an observer, want to figure out whether this process is totally random or not. One way would be to actually make a prediction, have some model that predicts what state this process is going to spit out, show that it's not random, and then actually do a measurement and see that indeed it matches your prediction. But if you don't know what the prediction should be, then just looking at one sample from some supposedly random process doesn't really tell you how random it is. Like if I have some random number generator on my computer that spits out a number between 1 and 100, and I use it, I run it, and it spits out 7, I don't really know from that whether that process was actually random or not, right? Because it could have been that it randomly produced 7, or it could have been that by some deterministic process it came out with 7. So what could you do? Well, you can make 2 identical computers in exactly the same state, and then run the process on both of them and see if you get the same thing on both the computers. And there's a version, and then if you do, then with pretty high confidence, you know that it wasn't actually random, right? If you get 7 on both, then probably this is secretly a deterministic thing. So you can do a similar thing in quantum mechanics. It's called a swap test. Roughly, you take your 2 copies of this quantum state, and you swap them over, and you see if you have the same thing that you started with. So we can do this for the radiation. And naively, it seems like the more radiations we swap, the more different the state is that we end up with than the one we started with. And this has to do with the fact that the radiation is entangled. Again, we could get into the depths of this, but I sort of want to avoid doing so. The radiation is entangled with this region that will become the island in the interior of the black hole. So it ends up looking quite different from what it looked like before. But there's also some probability in quantum gravity. Then very weird non-classical things can sort of automatically happen. In quantum mechanics, anything that's dynamical can break all the laws of physics. like it can tunnel through a barrier it's not meant to be able to tunnel through, and through a particle, and so on. And in quantum gravity, the dynamical thing is the sort of geometry of space and time, right? And so we should expect that processes are allowed that sort of cause the geometry of space and time to tunnel from one geometry and another geometry in a way that wouldn't be allowed according to the classical laws of physics. And it turns out that one of the things that can happen is what's called a space-time wormhole forms that basically takes the island in these two copies of the black hole and swaps them over just by some dynamical spontaneous process, like some particle is heading towards a barrier and it just spontaneously ends up on the other side of the barrier. The laws of quantum mechanics allow that to happen. And when you take into account the corrections from that swap happening, you realize that actually how similar the state you end up with to the state you started with starts getting bigger when it's more than half a Bragg-rated. So that's the signature, that's the observable signature that was meant to tell us how noisy the radiation is. So this calculation, by just doing some concrete observable that we actually expect to make concrete sense, is telling us that the information must be getting out of the black hole. So that level, what is the island? It's just the region that gets swapped by this wormhole if you try to measure whether information has been lost. And there's other measurements you can do as well that are fancier, that are things like Suvrat was saying, where you have some operator on the radiation that you're trying to make do the same thing as an operator inside the black hole. In that case, the wormhole that forms, basically the definition of your operator involves a simulation of a black hole. A wormhole forms mathematically. What this means is somewhat unclear, between the interior of the real black hole and the simulation of the black hole. And that lets you manipulate the interior of the black hole using the simulation. So again, the significance of the island is just, it's the region that can be pulled through a wormhole, and so it's the region that can be affected in this way.
Okay. So maybe I can say, I can give a different picture, Vasu, if this is a good point where, we could, so I'm going to give a slightly different picture, and then maybe I'll come around at the end and try and explain, how it's consistent with what Geoff said. So if you were to ask me, if this is a very useful picture to have up, because if you were to ask me, what is the region in the bulk that's dual to sigma rad, right? And I'm imagining that this is really a black hole in flat space. In fact, I think this is the long review by Malesena et al., right? By Almeri et al. So this is really a black hole.
Could I just ask what you mean by sigma rad here?
Just what.
Do you want me to scroll down to that?
The region is marked as sigma rad.
Yeah. So I mean, this paper is somewhat intentionally slightly vague.
That's fine. That's I'll come to what you say.
I don't think the claim, to be clear, just to clarify my claim. My claim is not that the island is dual to the region containing the radiation. My claim is the island is dual to the radiation.
I understand.
Which is in some region, and we can call sigma rad.
Yeah, I understand. I just want to give the alternate picture since you just so listeners have both pictures, and then I'll explain, as I said in the end, why what I'm saying is not inconsistent with what Geoff said. Okay, so I'll say that at the end. So let me preface again. So sigma rad now for me is I want to think of the region that's marked there, sigma rad. And in fact, in this paper, that's what we are talking about, right? There's some observer who can make observations in sigma rad. Then I would say that this observer has access not only to sigma island, which is the region that's marked in blue, but in fact to the entire region. So this paper suggests that this observer in sigma rad, or this picture might suggest, if one is not careful, that this observer in sigma rad can know about sigma island, but not about the intervening region. And I would say that you can always know about the intervening region. And so the alternative picture would be that this information about what went into the black hole is always outside. And it's not that there's an island, but rather, if you really have an ordinary black hole in flat space, the island kind of expands and goes out and meets the radiation region. So I want to explain briefly, without going into technicalities, what the picture is. Why is it that one would come to this conclusion? So, there's a standard way in which we think of how information is localized, right? Which is you throw something into a black hole, and then you imagine that you don't have access to you throw a diary into a black hole, and then now you imagine you don't have access to the information in the diary anymore. However, even in classical gravity, we realize that there is some information that you do have access to, which is just the mass of the diary, right? You threw in the diary, you still know what the mass of the diary is. Now, this information I want to note is now harder to access than it was earlier, because earlier you had the diary, you had access to the diary, you could have measured its mass in different ways. Now it's gone into the black hole, and you have to tease out the difference of the mass of the black hole and the diary and the old mass of the black hole. So it's harder to access now than it was earlier. Now, it turns out if you examine this picture quantum mechanically, and I think this is something that, if you examine this picture quantum mechanically, you find that not only do you have access to the mass of the diary, but in fact, if you keep track, not just of the Hamiltonian, but of fluctuations of the Hamiltonian, and also of, how those fluctuations correlate with other observables that don't commute with the mass. If you keep track of all of that, then in fact, you always have access to all information in the diary. It's much harder to access, of course, than it was when the diary was with you locally. And you can estimate how much harder it is to access. But that information is always available. Okay? And this seems to be a general property of gravity, which is, you in ordinary non-gravitational theories, you send some information inside a region, and you can do it in a way that no trace of that information remains outside the region. But in the theory of gravity, if you keep track of all observables outside the region, such as, and outside would be sigma rad here, then you always have access to the information that went inside. It's much harder to access than it was earlier, but you always have access to that. Okay. Now this follows from some careful analysis of the properties of gravity by looking at what the properties of low energy gravity are, and then making some careful extrapolations to the UV theory. In a sense, it's not very different from the kind of philosophy that's adopted when we do the Euclidean path integral, the replica trick to get the entropy. Because the Euclidean path integral is clever, so it knows about some non-perturbative aspects of gravity. Even though you could have said, you're just doing some gravitational computation, the Euclidean path integral is clever. And in the same way, low energy gravity is clever, and if you carefully extrapolate some of its properties to the UV theory, you would end up with this conclusion that I just said, which is that the information is always outside. From that perspective, some of the picture that Geoff described in the beginning about the information coming out would be mistaken, because I would say that the mistake that was made in Hawking's argument was to assume that the region inside, the Hilbert space inside, factorizes, the Hilbert space inside and outside factorizes. And that was really, if you look at Hawking's original argument in breakdown of predictability in gravitational collapse, that was really what his argument was. Sometimes people think his argument was he computed some radiation and said it was thermal, but that's not what he really said. He said, that could have been corrected, but because the Hilbert space factorizes up to these constraints of mass, charge, and angular momentum, you need to trace out over the degrees of freedom inside, and that's why you get a mixed state outside. So that assumption of factorization is very critical, and I would say that was a mistake that was made. And I think that's, in fact, the same assumption that goes into this derivation of the Page curve, which is, which assumes that you have some degrees of freedom inside and some degrees of freedom outside. And once you start once the black hole has evaporated, more than half evaporated, then you start seeing information emerge, because that's what would happen in a non-gravitational system. In the beginning, information would not be accessible in this region sigma rad. You wait for some time, and then information starts being accessible in sigma rad. So I would say that the same assumption went into deriving the Page curve. And so I would say physically the correct answer for a black hole is that the information is always outside. Now, as I promised at the beginning, I want to explain why this is not inconsistent with what Geoff said. So I think we can get, of course, back to the picture we have of, of the Page curve. And the way we do that in this case, and this is what Geoff was saying in the beginning, is if you, and Geoff can correct me, of course, but I'm going to try and say what I think what I think Geoff thinks, and then he can correct it, is that if you look at sigma rad, then you could discard some degrees of freedom. In particular, one of the degrees of freedom that I wanted to keep track of was, the energy of the black hole, and not only the energy, but quantum mechanical fluctuations of the energy and correlations of those fluctuations with other observables. Now, those are not what you would usually call the radiation. So you could try and just remove the energy from the set of observables that you're measuring in sigma rad. And in fact, in this picture where you're in flat space, there's a precise way to just throw out that degree of freedom from the algebra of observables and all its descendants. If you do that, then you do get a Page curve. So that's one way you could get a Page curve in flat space, by discarding some parts of information. Alternately, in many models of gravity, in these W holographic models of gravity where many computations have been done, what happens is that the graviton becomes massive. And when it becomes massive, then there is no Gauss law anymore. And because there's no Gauss law, the energy is not an observable at infinity anyway. And so, that's another way you could get rid of it. But even without making the graviton massive, if you just chose by hand to throw out some degrees of freedom, then you could come back to the picture that we had about the page curve. The question maybe that we could discuss is about whether the page curve is crucial for understanding what happened. And I would say that the page curve might give a misleading picture of what happened. It suggests that information is lost and then emerges, which you can make true by looking at only some aspects of information. But perhaps I would say the more accurate physical picture would be that information is not lost. And that's in fact the interesting aspect of gravity and how it localizes information.
So Geoff, would you like to respond to that? I mean, you did preface
by... So I let me start by saying some things Suvrat I agree with. It is certainly true, we have known since 1997 that in particular theories of quantum gravity, namely ones with negative cosmological constant, then the algebra of observables infinitely far away at the edge of space, in fact, contains all degrees of freedom describing the space-time at all times. This is certainly an uncontroversial statement at this point, at least in that context. So this is known as holography. It's this idea that gravity is equally the degrees of freedom in a gravitational system are in one dimension lower, and they're actually, one way to think about them is localized at the edge of space-time. It's in flat space and other space-times, we do not have anything like that as of yet. We do not know how holography works in non-perturbative quantum gravity. It is true, as Suvrat said, that even working with semi-classical gravity, there are signatures, specifically this thing that energy can be measured far from the black hole, and so should be in your algebra, that suggests that any non-perturbative quantum theory of gravity, any full UV complete theory of quantum gravity, which we don't yet have, should still be holographic. So information should be available at infinity at all times. I would call both of those claims pretty uncontroversial. I would say the most controversial part of what Suvrat said that I think most people would just find wrong, but in a sort of trivial way, is a definition. And that's the definition of what the radiation from a black hole is. So by radiation, I mean some photons going out. So if let's say we have some microscopic black hole that's, has a Hawking temperature that's visible, be some tiny thing, atomic scales or less, and you could see it. It looks like a very faint LED. It would just about be visible. It would be emitting light. And we could absorb that light. We could absorb that light into some fiber optic. We could put it in a quantum computer. We could collect photons one by one. We'd get a photon about every light crossing time. So, every nanoseconds or whatever. No, what am I saying here? Whatever. Frequency of visible light. I forget what it is, but it's pretty short. There'd be quite a lot of photons, but we can collect them all. Maybe we miss a few. I don't really care if we miss a few, honestly, but we try to collect these up in our quantum computer. And then I want to talk about the state of those photons. And that to me is the radiation. And I don't even care if we got all of it. We get as much as we can. For the page curve, it doesn't really matter, because if you miss a few bits, then maybe it's a bit hard than it otherwise would be. But that's the question we're talking about here. I'm not sure where the entire energy of all of space and time ever comes in as part of that radiation, right? These are ordinary, these are just some photons. They're light. We know how to talk about the quantum mechanics of light, the state of light. We should be able to ask questions about this light we create. We should be able to ask about its entropy. That's what the page curve is meant to tell us. So I think Suvrat thinks that what that curve does is less significant. When we do quantum state tomography with the photons we've collected and we work out what state they're in, he thinks that's less important a question than the fact that gravity is holographic. I think he's probably right on that. I think quantum gravity being holographic is probably the single deepest, most important insight we have into it. But it's a different question. And it's not the question that anyone has meant by the page curve, certainly in the last 25 years since ADS-CFT. So when maybe you say you don't care about the page curve, that's fine, Suvrat. You don't have to care about the page curve. But when you say there is no page curve, then that's just like
well,
denial of what it in practice means and has always meant.
Yeah,
at
I want
least
to make a
since
stronger
1997.
Yeah, I want to make a stronger statement. So that's I think a good point to go off on. So, the issue is, I think a lot of the discussion is phrased in this language we're familiar with, right? Which is the photoelectric effect. You have some photons which come out. There's some well-defined photons, and you measure them and you collect them in a quantum computer, and that's kind of appealing because that's something we're used to. We're used to qubits, which you can separate and you think about it. But if you think a little bit more about how how a black hole would really behave and how you would have to recover information from a black hole, it's not like the photoelectric effect at all. In fact, you would have to make measurements to very accurate precision. So the kind of observables I'm talking about here are just that you have some detector in sigma rad that measures fluctuations of the electromagnetic field and also their entanglement with fluctuations of the gravitational field, right? And so it measures these things, and then it tries to recover what information was there in the black hole. So that's, I think, a more precise way we could talk about it. In fact, we do have a precise language to speak about that, and that's to speak of the algebra of observables in sigma rad. And so I'm always uncomfortable when people retreat and to this comfortable language where you can speak of qubits that are well-defined, because I think that misses the picture. Now, let me say something more quantitative about this algebra of observables. You see, you're trying to detect photons at an energy which is given by the Hawking temperature, right? So you have to be sensitive to that. Okay. Now, if you wanted to recover the information, you would have to make measurements to exponentially precise accuracy, to accuracy e to the minus s. Okay. Now, usually, if you just have a bunch of 10 qubits and they're evaporating, you can you can decide that you want to measure something to accuracy 2 to the minus 10, and that's fine, right? And you don't have to care about gravitational effects in that. If you think, however, of how the order of limits for a black hole goes, you will find that gravitational effects in this setup are controlled by G Newton times e to the d minus 2, okay? Where E is the energy of one of these photons. And a black hole is a unique system where that parameter is 1 over s. Okay? That's not true for any other system. But for a black hole, it is true that gravitational coupling, the strength of gravity is also controlled by the entropy. So you can't take the entropy, can't keep the entropy finite while forgetting about gravitational effects. What that means is that this detector, which is sitting in sigma rad, which is trying to, detect fluctuations of the electromagnetic field and gravitational field, will also have to be sensitive to these gravitational effects. So such a detector, what I would say, and I think the physical statement would be, if you really set up a detector that could make measurements to the accuracy that was required to recover the information, then such a detector would also be sensitive to these gravitational effects and would see information at all times. And that comes just from the simple estimate of how strong gravitational effects are, and the fact that you can't ignore these gravitational effects while you keep track of radiation. And these observables would be as natural. Yeah, just one last thing. Sure. Would be as natural as anything else, right? Because what you measure would be, say, the Riemann tensor. And one of the components of the Riemann tensor would give you the energy. So in fact, to throw out the energy would be by hand removing some information that you can access. So I think it's important to be careful about what observables we look at and what the algebra of observables is. And if you do that, you see that it's not so easy to define an algebra which is sensitive to the radiation and sees a page curve, but doesn't see information at all times. But yeah.
So
I totally agree, Suvrat. Sorry, go ahead, Vas.
Yeah, no, I just wanted to see if I understand like what's behind Suvrat's statement. Are you alluding to some kind of gravitational dressing that the photons actually incur? No. And that's what's no?
I was trying to estimate. I was trying to estimate. So there are these unusual effects I alluded to in gravity, which have to do with, just to say one more thing, the way we understand these effects is not by invoking ADS-CFT, as Geoff pointed out. If you invoke ADS-CFT, a lot of these computations of the page curve and so on kind of trivialize, because we know there's some non-gravitational dual which has a page curve. And similarly, we know there's holographic setup where all information is around. But rather by just trying to understand what are the correlation functions that in gravity could detect information at all times. So what those correlators are some correlators of the Hamiltonian and other observables. Right? Now you can ask, what are they suppressed by, right? How weak are those correlators? And so the coupling constant that enters there is the gravitational coupling constant, which is dimension full, of course. So the dimensionless coupling constant that enters there is
sure.
G2 times e to the d minus 2. Now that constant for the black hole turns out to be 1 over s. So if you keep track of s point correlators with 1 over s, with this coupling, which are roughly suppressed by e to the minus s, or 1 by s to the s, then you would see all information at all times. But that's also the accuracy you need, if you try to measure other degrees of freedom and try to not keep track of the Hamiltonian. So for the black hole, there isn't a natural division of complexity between what you need to do to see information at all times and what you don't. There are other examples, in fact, we can see this, but one such example is, in fact, the small black hole in ADS. If you think of a small black hole in ADS, and you let it form and let it evaporate, you could ask, what are the degrees of freedom you need to keep track on the boundary so as to see a page curve? And there, you know what's happening. You know that at earlier times, what's happening is you have two blue balls which crash into each other. They form some quark gluon plasma, and it decays back into blue balls again. Here I'm taking some holographic picture of the small black hole. At the beginning, it's very easy to read off the information. In the middle, when the black hole is there, it's hard to read off the information, but the hardness is given by e to the minus s, where s is the black hole entropy. If you wait for the black hole to evaporate, the difficulty of getting the information is now e to the minus s prime, where s prime is the entropy of the Hawking radiation, which is larger than what it was when the black hole existed. Right? So in fact, the second law of thermodynamics tells you it's not easier to get the information when the black hole evaporates. In fact, it might have been easier to get the information before the black hole evaporated. So I think that it's not just a formal statement. Yeah.
Can we take a step back here? So let's say we have a black hole that has a Hawking temperature of a few thousand degrees or whatever it is, and it's emitting visible light. It's like the sun. It's a lot weaker than the sun. It's a tiny little sun. It's about it would just be about visible to you or me here. Okay.
Okay.
The question is, can we collect some photons from that in a coherent manner, keeping their quantum state from decohering, or are you claiming that the gravitational physics, let's build a big sphere around that black hole? I don't think it needs to be terribly big, but I can make it big if you want. I could make it thousands of miles across or something, but let's get it vastly outside of the range of gravitational attraction in the black hole. Let's put it in the space, so the black hole is just floating there. We build our sphere around it. We try to collect a photon. Do you agree that we can do that?
Yeah, so just to say one, there's some 1 over r that's irrelevant, right? Because all fields are going to die off as 1 over r. So both the gravitational field and the electromagnetic.
The question is, can we collect the photon?
Yeah, so good. Of course, you can collect the photons. The question is that what is the accuracy that you need? And the accuracy you need in order to have a detector that gets the information is e to the minus s.
No. Forget about how accurate we're being. I'm happy to be as dirty as you like. I'm happy to get the photons. Each photon, there'll be some order 1 perturbation to it. Okay? I just want it pretty good. Or 99% accuracy.
I mean, you don't want to just keep track of the number density of photons, right? You want to keep track also.
I want 99% accuracy. I want to collect them. I want to collect it with 99% coherence, and I want to store it in a quantum memory.
Right. So you want to preserve.
Then I'm going to leave it there.
You want to preserve the quantum.
No, I'm not observing it. I'm not observing it. I'm coherently collecting it and storing it in a quantum computer in some quantum memory.
Yeah, I said preserve the quantum state.
Yeah. Oh, sorry. Preserve. Yes.
When you preserve the quantum state, you need to have some detectors that are sensitive to e to the minus s corrections.
Where is s coming in here? I'm collecting one photon.
Coming in because I want to preserve the quantum state up to some accuracy, right? You want to transfer the quantum state from the space-time into some quantum computer, and the fidelity of that transmission has to be e to the minus s.
I want fidelity of order 1. I don't care about e to the minus s.
I don't know what
I'm asking. Can we do this with fidelity order 1?
Sorry, in terms of observables, like what
fidelity
is
order epsilon? Forget about observables. I'm collecting one photon, Suvrat, and trying to store its state in quantum memory.
I think this is a very misleading picture, which is why I feel we should talk.
How is it a misleading picture? It's a light source. We do this all the time, Suvrat.
Exactly. We do this all the time, and we never. No, we do this all the time, and we never recover. If you burn a piece of paper, you can collect the photons from that. You don't recover what's written in the paper.
I'm not collecting all the photons. I'm collecting one. I'm trying to capture one photon from this source coherently. With order 1 fidelity.
If you want to look at the number density, of course you can look at that. I don't know why we are shying away from what is the observed quantum mechanical.
I'm not talking about the number density, Suvrat. I'm talking about collecting one photon and coherently storing it in a quantum memory.
What does that mean?
Can we do that?
Can you tell me what is the observable?
We collect that photon, we coherently put it into a fiber optic cable. So now we've just
Okay, I'll make this precise. There are a set of correlation functions which you can measure on this Dyson sphere, which correspond to insertions of the vector potential. And your quantum computer will keep track of all of these correlation functions. At the end of it, your quantum computer will give you a readout of what all of these correlation functions are. Yes, you can do that.
Here's what I want to happen. I want to have photon comes out, it's delocalized, it's some low angular momentum mode, right? Yeah. But I want to be able to coherently absorb it with I'm allowing order epsilon error. I want like 3 nines or whatever I can do right now.
What does that mean in terms of the electromagnetic potential? There's some wave functional for the electromagnetic potential, and what are you keeping track of? I think this is this is why I find this this is my objection to this whole picture. Is in the photoelectric effect, what we really keep track of is the number density. So this is a very precise question, right? What correlator are we keeping track of? I mean, that's a question we should be able to answer. Why do we have to?
We don't measure correlators. Like we
measure correlators.
We have some detector, we have some antenna or whatever, and we want to absorb the photon coherently.
You can tell me quantum mechanically
some system with probability close to 1. That's all we need here.
What is the Hermitian
observable getting involved?
What is the Hermitian observable that this antenna is sensitive to? That's the question that you have to answer. You can't say I mean, we're using the word photon as if that's well defined, but what is the Hermitian observable?
Yeah, so we're looking at S-wave fluctuations outgoing and hitting this Dyson sphere or whatever it is.
The observable is the electromagnetic potential?
We're not. Look.
No, you have to answer the question.
Okay,
of what
so let's say that we just hook it up to some fiber optic setup. Where's it going, Geoff?
I think
what is the thing at the end of the cable going to do?
No, because I think the problem is the moment
put it in any quantum computer, some quantum memory.
Yeah. So the problem is that the moment we transfer, we do this thing where we have this radiation, which we imagine is well defined, like the photoelectric effect, and transfer it to some quantum memory. I think we've lost the question of what were the Hermitian operators that what were the quantum mechanical observables that we are sensitive to? I think that's an important question. And in this question I said about the small black hole, it's a very precise question, right? You look at the CFT and you ask, what is the set of observables that you have to keep track of that will see the page curve? That's very precise. We can't say, well, we turn on a fiber optic cable and we won't answer that question. We have to answer the question.
I would say it's much more precise to talk about a concrete experimental setup that is collecting photons, which is a very standard thing that we do all the time, and we collect them coherently.
I disagree.
And we bring them together.
No, I disagree. We do it because I think this everyday intuition we have is intuition from the photoelectric effect, where what we actually do is keep track of number density. Was there a photon there or not? And
no, that's not what I'm talking about. I'm talking about, say, okay, if you're generating entanglement by sending a photon down a fiber optic cable, you're coherently absorbing the photon at the other end, and you're storing it in some quantum memory.
Good. In all of these setups, I think we should be able to answer the question of what is the quantum mechanical observable we are measuring. I don't know why we don't answer that question. We should answer it here. In ADS, in a small
the final one observable I'm talking about is a Pauli, say some Pauli operators.
So is it like
computer that we eventually got into?
Good.
Yeah, we store it in some finite dimensional system.
Geoff,
store it in some each thermal photon in like each.
Good. But when you measure this Pauli observable, there are go on, Vasu. Yeah.
So let's just make this more. So you said it's an S wave, and then are these
then we get it
corresponding to some kind of like just the helicity states or something? Is that what you want to?
We got it. Yeah. So we got the fiber. Okay, great. We collect the S wave up. We put it into some fiber optic cable. It's still that's a pretty standard transformation. It's still a one-dimensional, 1 + 1 dimensional mode, and then we steadily absorb that into some. Collected into some finite set of oscillators. We can even just have it going around in a circle if we want for a long period of time, and we have quantum boosters and stuff that maintain coherence. I think we just get it in some quantum memory where we can stick it around.
I think we're doing things which are not precise, and I think this is especially when we discuss.
I mean, you want me to build this thing, Suvrat? What do you want?
No. I don't want you to build this thing. I think the question is very clear. Take a small black hole in ADS. There's a set of observables which we understand very well. Right? It's just a set of observables which you get by looking at boundary operators and looking at products of those operators. Just tell me
I don't
what
live
set
at
of
the boundary,
observables you want to
Suvrat.
look at.
No,
I don't live at the
go back.
boundary. I
Let's just
live
go
on
to the
Earth.
end of what Geoff said. So he said
Okay,
that
go
in the
on.
end
Yeah,
he wants to measure some sort of like poly operators, right? And presumably that's like some
Let's just leave it
discrete,
in the
like it's
fiber
just
optic cable, going around in a loop along some fiber optic cable. You know, you can put boosters in to stop it decaying and so on, but it's just sitting there, and then we're just going to get more and more of this in the loop, and then we can do some swap test. We basically do a Hermitian observable that is swap the state of one fiber optic cable with the state of another fiber optic cable from another black hole really far away. That's an observable. That's a Hermitian observable.
Does this detector that you have?
I'm asking what's the expectation of that?
Yeah, I still didn't understand what there was some original quantum field theory which we had defined in the black hole. And I think we've completely lost track of what the observable.
But maybe we can do it, right? Like maybe it's just like maybe it's just as simple as you have. I mean, it's momentum dependence,
you literally
S
just
wave,
absorb
and then
it
it's
and
like the
collect
helicity state or something like that. Like let's say the helicity state is your bit, presumably.
Excellent.
Right, like I don't know. Is that what you want?
Excellent.
Or
Is
there something more?
We need more than that because there's also the location of the photon.
No.
Okay,
But we have some mode. There was a 2D mode.
Yeah, I agree.
That is the S-wave mode that is coming out, right?
So it's spinning around in the loop. That's the
right?
space-time dependence. But the swap you're going to do. Okay, sorry. Yeah.
Let's say we look at the electromagnetic field, right? And it has some dependence on R sigma. When I say I measure A of R sigma, does that mean in my quantum computer there's an observable that I can measure that will have the same probability distribution as this A of R sigma? Is that what we're saying? When we say we measure A of sigma, are we measuring its expectation value, or are we measuring? We're measuring it coherently, right? So we have this.
Yes. So everything's been coherent up to this point. We do this with the square kilometer array, for example, right? I think they're trying to.
Good. And do you also keep track of the Riemann tensor of the space-time?
No, I forget about that. Waste of time. Too much hassle. I don't even know how to do that. That seems like really, really hard. I know how to collect photons. So let's forget about that.
I don't think it's any harder because I think this is once again, I think the issue here is we have this language used for everyday language, which is where gravitational waves are much harder to collect than electromagnetic waves.
Yes.
But if you look at the accuracy with which you need to retain coherence for these photons, it's exactly the same.
I don't want this high accuracy, Suvrat. I don't need this high accuracy. I want order 1 accuracy.
I don't see how you
I'm then going to ask you what curve I'm going to get. I don't care about exponentially high precision. I don't care about getting all the radiation.
If you haven't
all I'm going to do is I'm going to do each step with order 1 accuracy. I'm going to end up with 3 systems. I'm going to end up with the radiation I managed to collect. I'm going to end up with the black hole or whatever. And I'm going to end up with an environment that's all the noise I lost. All I need is the environment to be much smaller than the radiation, and I'm good.
No, I think
I can give up on all gravitons. I can have this. I can give up on all sorts of stuff. I can do a terrible job, and I will still have this.
No, I think
sorry. Let's just maybe we can make this easier for Geoff to make this. So let's put it this way, Geoff. Like if it weren't a black hole, right?
Yes.
You were just collecting it from the sun, right?
Yes.
So what exactly would you want to do? So you said that okay, you will collect. Let's just go down to the observables that Suvrat wants, maybe, right? So we have like some S wave that subsumes the space-time dependence of the state, and then we have some helicity state, and then we're going to make some measurements of correlations between
the S wave.
The
S wave is a 1 + 1 dimensional field, right? We have mode numbers, wave packets labeled by K and their approximate location or whatever, right? We can transfer each of those wave packets into a fiber optic cable. That is totally a thing that can be done. It's now moving down a fiber optic cable. We will have some loss as we do so. Let's say the loss is 0.1% or something pretty good. Okay.
Whatever it is, yeah. Let's just look at that.
It just needs to be a lot less than half, basically.
Okay.
Well, it needs to be maybe less than. Okay, you've also got some gravitons. We're giving up on the gravitons completely, so they're a loss.
We've forgotten the gravitons. Like they're gone.
10-20% gone right there.
Sure.
Yeah.
So no, now there's no black holes. The sun. So we got these photons, right?
Yep.
And now we're going to measure. Okay, fine.
Yeah. Now let's just do this for a little while. Let's create something with an average number. Do it for an amount of time where the expected number of photons is like 1,000 in there or something.
Okay, great.
Right.
So we collect 1,000 photons. And then?
Great. And then now I'll make my concrete emission observable that is just an observable on 2 of these fiber optic cables. It is literally just take each point along the fiber optic cable, the electric field or whatever, and swap it with the electric field on the other fiber optic cable.
Okay, so we're doing correlators now. Okay, fine, right. So we have an observable in terms of,
I'm not being concrete about how I do this experimentally, but experimentalists do this.
I think this is very misleading, because we're talking about a precise setup, and instead of talking about something that we do know precisely, we're introducing these fiber optic cables and so on.
Well, I think the fiber optic
I
cable
know what a fiber optic cable is. So I don't know what infinity is.
Maybe I can just write something briefly, like this is one time.
Sure.
Okay. So should I try to share the?
So I think that Geoff answered your question though, because he wants to measure correlation.
This to order one.
So let me ask the question the following.
Let's set aside the order. So the observable, right, is electric field, two-point function or something like that, or whatever.
Two-point function, not
a two-point function, but it's just a swap.
Because what he wants to measure is what the swap test is going to measure is trace of rho squared. The swap test is going to measure trace of rho squared, right? The swap test is going to be sensitive to trace of rho squared. And you want to check, so it's going to check purity for you. So it's going to check whether trace of rho squared is 1 or whether trace of rho squared is something else. However, in terms of the original variables that you're measuring, and you can see this, it's hard. There are different states which, for all measurements of the electromagnetic field, look exponentially close to each other, and one of them is pure and the other is not. That's why it's so hard to tell pure states from mixed states. So we pretended that there's a 2-point function that would tell us purity.
Well, it's not a 2-point function.
No, it's not a 2-point function.
It's an exquisitely accurate measurement, because it's distinguishing a pure state from a mixed state, and pure states and mixed states are very hard to distinguish. So and we've lost, and so in this description where we had this photo, we lost track of the exquisite precision that was required.
No. So here's the thing you're missing. In the final process, when we finally do the swaps, we do need exquisitely high precision. Let's say a black hole had 10 to the 20 bits or something originally. Make it smaller, make it million bits. So it's going to be very high wavelength fast stuff, ridiculously high intensity gamma rays, but we can probably build some machinery that does that. We're theorists, not experimentalists. We collected this up. Yes, at that point, once you're doing the swap, you do need to do the experiment lots and lots of times. That's basically all you need to do to get that precision. But you need to have all the experiments be exactly the same as one another. If the experiment's a little bit different from one another, and so, okay, it's important the two systems are really, really, really precisely identical. That is true. Because if they're a little bit different, then the differences between the states from the processes will matter. But it is not important that we got the original modes we wanted with high fidelity. It's only important that we got the original fidelity modes that we wanted with fidelity order 1, specifically that we got most of the energy and entropy of the black hole ended up in this system. Once we get more than half, we're good.
Let me say the answer in this way, maybe to the question that I was asking, and let me see if Geoff, let's say we do this in flat space, right? And so I'll tell you the answer I was looking for. So there are some degrees of freedom which correspond to modes of the electromagnetic field. Right? And there are some there's an algebra of observables that corresponds to modes of the gravitational field. Right? There are two kinds of modes. One of them are what are called the news operators, and the other is what is called there's something called the Bondi mass. And what Geoff is wanting to keep track of is all correlations of the electromagnetic field, because in the end, this high fidelity, I think this fiber optic and so on is very misleading, but because in the end, what we should be able to reconstruct from whatever we did, right, are all possible correlations up to accuracy e to the minus s of these electromagnetic field operators, including higher point, 4-point, and S-point correlators, right? We have to keep track. That information we can't lose. If we lose that, we lost track of whether the state was pure or not. So in the end, whatever we did, these fiber optic cables in this quantum computer knows about S-point correlators of the electromagnetic field up to e to the minus s. Whether we do it by trace of rho square or not is irrelevant. However, I think it was important that we did not keep track somewhere of the energy. And so somehow you want to throw out some set of observables in that. And that's I think what this fiber optic cable is effectively doing. It's looking at some algebra of observables, which doesn't keep track of the Hamiltonian. And this is just a way to do that, right? To say, well, we won't keep track of the energy.
Certainly, look, I don't think that we can measure the energy of the system by measuring the metric in practice to very high precision at all. So that seems quite hard to use in practice. I'm certainly happy to talk about an algebra at infinity like you want. So in flat space or whatever, we can do that. And I agree in that case, if you have the Hamiltonian, then you have the full algebra, you have everything. If you don't have the Hamiltonian, you have something that follows page curve. We're happy to agree on that. To me, the much more interesting thing is what could you actually do?
I want to say something more actually about the algebra.
Yeah.
So could I say something more about the algebra? The sharper statement about the algebra is you could try to coarse grain the algebra now. And if you give me the sun or you give me a set of qubits. Yeah, sorry. Let me say something. If you give me the sun or you give me some set of, I could coarse grain that algebra. So I could say, well, I'll keep track of, for a system of 10 qubits, 10-point correlation functions up to accuracy 2 to the minus 10. And I'll throw out all other observables. So that's the truncation of the set of observables I'm allowed to measure. That coarse graining will see for a non-gravitational system, the page curve, because it's not sensitive to gravitational effects. For a black hole, there isn't a natural coarse graining of the set of observables at infinity that will see the page curve for you. And I think this is very clear when we discuss the case of the small black hole in ADS. And that's why I feel this is a really sharp question that we can focus on. It's a mathematically precise question that doesn't involve, appealing to pictures of the photoelectric effect and collecting things in a quantum computer and so on. It's a mathematically precise question. We have a set of observables. We can, in fact, be in some ADS CFT setup. We can ask, what is the truncation that we need to do in order to see the page curve? And in fact, I can tell you what the truncation is. It is you throw out some set of observables.
Nobody's doing this truncation except for you, Suvrat. Sorry.
If it's not the truncation, there is no, you're not telling me what is the set of observables that give you the page curve.
I just gave you one. I gave you an experimental setup and then I gave you a precise observable.
Please, can you
say
final
observable we needed exponential precision for. The process of constructing that observable, of ending up with these two fiber optic cables, we did not need exponential precision for. In fact, we only needed precision more than half.
Setup, can you say it in the original setup without introducing the fiber optic cables? There's an algebra at infinity. What are the degrees? What set of observables in the algebra do you need to include to see the page curve? I think it's the same
flat
answer
space at infinity. In
flat
space at infinity, there's a closed algebra that doesn't include the Hamiltonian.
Excellent. So that's the algebra.
So then it's fine. We can do that. It's a closed, but it doesn't need any coarse graining.
Absolutely, we agree with that. That in flat space you discard the Hamiltonian and there's a closed algebra that you see that sees the page curve. So that we all agree with. Okay. So that algebra does not include. So there's a way to throw out the Hamiltonian from the degrees of freedom, and that's what I said at the beginning. And if you do that, you choose to discard some information, you would see, see
again, the Hamiltonian is not radiation, right? When no radiation has got out to infinity, the Hamiltonian is already there. It is not the radiation by any definition.
Sorry, can I say it's a component of the metric? In fact, if there's just to point out.
I want to forget about the metric. Gravitons are tiring, so I don't want to deal with them.
No, but
consider a no graviton page curve.
Yeah, the gravitons are in this. Well, fine. I mean, you could forget about. Yeah. Anyway, I mean, the point I'm repeating myself, but just to say once more, these other observations that you're making, the accuracy that you have would be naturally sensitive to the metric, and you're choosing not to measure some degrees of freedom because these other observables would have to be sensitive to very small fluctuations of the electromagnetic field.
No. So I think that this is where the disagreement really is. So basically, I think, okay, so maybe we can sharpen this. We'll keep the fiber optic cables for now, but anyway, what Geoff said was that for his final swap operation to actually see that, oh, well, the information was there, he would need very high precision, whereas to actually obtain the photons, right? So to basically to accumulate this observable that he wants to do the swap with at the end, he would not need a very high precision in the manner in which he does it.
Good.
Perhaps that's where we can. Geoff, do you agree that this is
yes.
Okay.
Good.
Okay. So let's try to sharpen.
Can I share screen for a minute? Just to say this. I think
yeah,
maybe you can see screen. We can annotate your screen.
Why don't you go ahead? You should be able to.
I think you have disabled.
Oh, have I done that? That's not
but you
good.
can share and we can just both annotate your screen if that's okay.
Okay. So do you want a whiteboard or would you
A
like?
whiteboard is fine, right, if you like.
Okay, a new whiteboard. Here we go.
Yeah. So, yeah. We could do this in. Let me draw two pictures just to say what's happening here, right? And I really I feel that you can't see the other one. I see. Well, this is flat space, and let me draw the other one below. Sorry, you only see one, right? Do you see both the ADS and the flat space, or no? The other one is off.
The way you drew before actually made it more. Okay, let's see.
Yeah. So
let's put this in the middle. Okay, this should roughly be
good.
Okay.
So there's some set of observables here which are like A.
Yeah. Okay. I'll scroll to keep up with you. I'll follow you. I'll follow you.
Yeah. So this is some observables for the electromagnetic field, and then there's some metric, right?
Yeah.
This U is this coordinate that goes here, and omega is the coordinate that goes around. And I'm not writing the indices, right? And I think we should really say what we are measuring in terms of, in terms of this set of observables. And I'll tell you what. And the algebra that Geoff is referring to is the following algebra. It's the algebra where we keep track of A of, omega 1, U1.
Honestly, I'm fine with just keeping track of A and maybe the neutrino field.
Yeah,
I don't want to bother with H.
That's fine. And so we have to keep track of this algebra, and this is the algebra. So Geoff wants to keep track of all of these observables. Okay. Now the thing about these and you have to keep track of these observables, and you have to measure them. You have to keep track of these observables, and you have to, some of these observables have very small expectation values, and the expectation values are suppressed by some parameter, which is, e to the minus s. Okay. Now it's true, you can keep track of these observables, and you can say, I'll never measure the metric, right? Even though the metric is there, I will choose not to measure the mass of the black hole. However, remember the gravitational fluctuations, this is what I was saying earlier, are suppressed by, what happened? Yeah. Are suppressed by GE to the D minus 2, where this is the energy of the Hawking quanta. And that's also 1 over S. So what Geoff said is, I'll keep track of these observables. I mean, all the fiber optics and so on is effectively keeping track of all of these observables. And I'll keep track of them to E to the minus S. But here's something else you can measure. And, you could measure this guy, and this is also suppressed by the parameter 1 over S, but I won't keep track of it. And true, if you do that, you'll see a page curve. And
so
I agree with
the difference, Suvrat, is to measure the gravitational energy, the further away I am, the smaller it gets. That would also be true for A. If we just let the photons spread out, the more they spread out, the harder they are to collect as well. And so at infinity, it's sort of infinitely hard to collect them at all.
Yes.
But if you collect them with the fiber optic cable, that's not true.
No,
and
but this
just end up with some very, very long fiber optic cable, or you spread stuff out through space. You just need to keep the mass density low.
But let's. I don't know.
And then you're just taking a load of products of things.
No. The fiber optic cable is living on some
do.
Dyson sphere, right? Which is Dyson sphere is living on some radius r, and so I think we should really go back to this. This is the precise set of observables, and the Dyson sphere is collecting
I think that infinity. Yeah, I think infinity versus naught is not that important, just in the sense that, like, when we're in the radiation zone, we pretend like we're in infinity for all practical purposes.
So I think it's important because to define a sensible, like the ADM mass is really only defined.
We can define quasi-local masses. That's fine.
Like it's quite hard to. We can define quasi-local masses approximately.
And the point is that, like, we'll only ever make sense of those for all practical purposes in isolated regions. So I don't think that this matters that much. So all this to say that the question, okay, going back to this point of the precision versus the precision at what you capture versus the precision you need to be, or the kind of precision you need to actually do the swap operation. Let's just get back to that, assuming.
Yeah.
So Geoff, what you're saying is the setup just doesn't, it's just kind of unclear, right? In the abstract given whatever experimental setup we want, what it would mean to actually capture the gravitational observables of the kind that Suvrat is referring to here. Even if we say that like it's right.
Let me emphasize, I'm just saying compared to collecting photons.
Okay.
I'm basically happy to say, let's consider the observables at infinity and it includes everything.
I think that's slightly let me say something
bigger philosophical.
Well, let me say something we do in real life, right? Which I think I'm going to say something which is also misleading. I'll point out why it's misleading. What we really measure about a black hole is its mass, right? What we know about black holes in the world out there is mass. We don't know their radiation. So in fact, I could say, well, what we really measure about black holes is their energy and not their radiation. But that's a little, I feel like, that statement that, again, we measure photons, we don't measure gravity, because it's true that for ordinary systems, this parameter is much smaller, right? For ordinary systems, S and this are not coupled. And so it's true.
But Suvrat, I guess Geoff's point would be that like the analog of capturing the low precision information about the gravitational field you would need to eventually do the swap test when it's about gravitational degrees of freedom, that's what you cannot quite do the way you could do with photons. Like
so somehow the statement seems to be somehow the statement seems to be that it's much easier to design an experimental apparatus that can measure these observables to accuracy e to the minus s than measure observables with insertions of the metric to e to the minus s. I mean, maybe that's true, but I think
so the difference is one of them has to be done at a finite radius off from the black hole. The other one, once you've done the collection with some precision, you can make your quantum computer as big as you want. You can take as long as you want. So you should be able to do it without arbitrary high precision.
Well, I would measure the metric at this Dyson sphere that's measuring A is where you do the fiber optic cables. I would also use it to measure the metric. So somehow the statement seems to be that, one algebra is experimentally easier than the other one, but this I feel is not a statement which is I mean, I think
maybe this takes us back to the sorry. Go on, Geoff.
To me, the whole point of the page curve is to understand what information you have in general, from pretty general principles, when you only have some of the degrees of freedom. I was talking about photons because I think the photons are the easiest degrees of freedom to collect and then be able to manipulate precisely and learn information from. So it's easiest to ask about. But the page curve is fundamentally, you have some degrees of freedom, you don't have others. How do I see from the black hole physics that even though some degrees of freedom, when they're more than half of the relevant degrees of freedom, they carry information? I think you think once we've said information is always there and is always an infinity, then we're done and there's nothing else interesting to ask. And that is the most interesting question, right? Is the information always there? Is it infinity? And the arguments for holography based on semi-classical gravity are nice pieces of evidence that should be true in non-perturbative quantum gravity. And I agree that it's the deepest thing we know about non-perturbative quantum gravity. But it is also interesting to know if you only look at some of the degrees of freedom in some weakly gravitating region, then what information they carry. And the point of the page curve is any time you have more than half, whatever those half might look like, they might be photons, they might be gravitons, they might be neutrinos, they might be anything. Anytime you consider more than half, then they start carrying information and their entropy starts going down because of that. And that is the essential lesson.
Okay, I agree with that. Can we scroll down a little bit to the ADS picture? Can you see the ADS, the two vertical lines? I just want to say, can you see this, Vasu, also? And is this being recorded? Okay. So, I want to say something here. There's, of course, a page curve that we kind of always knew we could get, which would be the following page curve, right? You measure the entanglement entropy as a function of solid angle.
Scroll down.
Do I need to scroll down further?
No, I'm just.
For whatever reason, we're seeing different screens, but.
Sorry. Yeah. Okay, I see. Okay. I had to scroll down. Good.
There's, of course, a page curve you would see as a function of the angle theta, which would be what so this, once theta crosses half the sphere, you would start seeing the entanglement entropy go down. Now it's always true that if you look at more than half the degrees of freedom, if you have some division of degrees of freedom, you'd see the page curve. Now, what
this is ADS vacuum?
No, there's ADS black hole.
I don't think you get a kink in ADS vacuum.
Sorry, there's a black hole. There's a BTZ or something.
There's a black hole in the bulk.
There's a large black hole?
There's a large black hole
Okay.
above. So it's a thermal state.
Okay.
I'm just looking at it's kind of a trivial page curve, but of course you would see a page curve, right? If you went round as a function of angle.
Yep.
Now, this is something we knew about. And it's true, of course, if you look at more than half the number of degrees of freedom, you would see a page curve. The issue is, I think that my objection is not to any of the computations, which I think are nice, where you add on a non-gravitational bath, and that gives you a precise way, in fact, of separating the algebra that sees the page curve from the one that doesn't. In fact, in the fact that the graviton becomes massive is another way of throwing out the Hamiltonian in these setups where you have ADS coupled to a bath. I think my objection is more that when the page curve was derived, it was derived based on this misleading picture that information goes into the black hole and then comes out. And maybe I disagree with Geoff that if Geoff says that nobody believes that picture anymore, I think a lot of people think precisely in those terms. The information goes in some sense, and then it comes out after the black hole is half evaporated. And I think the page curve kind of, historically, that the error in that argument was not realized. And so it was thought that, influential people in the field said, to understand the information paradox, you need to get this curve. And that's why I think the page curves that have been derived more recently, which are when you couple things to a bath and then see a page curve, which is another way of looking at more than half the number of degrees of freedom, are I think they kind of they change the question so as to preserve the answer of the page curve. And so my objection is not to anything technically that's done in those computations. It's true you can define these algebras that see the page curve, but they give a misleading picture, I think, of how information emerges. But that's a question of perspective more than.
So, yeah, I guess the question of information, and maybe I'll just scroll back up here to the distinction. I mean, there's S here and S here, but I guess operationally, let's just see if we agree with this. Let's just see if I've understood the discussion we've had so far. Operationally, the top line here.
Maybe can I do the same thing in ADS if you scroll down actually?
Sure.
I think
I'd really rather not go to ADS. I feel like we're talking about could just
ADS is something we understand well, and maybe some listeners understand well too, right? So I think it's useful to say the same thing. Yeah, I think there's an interesting point there.
Okay,
I'll say the same thing, and you can say it again.
Sure.
Imagine this black hole was formed by the collapse of something, right? Like this, and then it later evaporated. Right. So this is T1, this is T2 when the black hole exists, and then there's time T3. And you can once again ask the same question. What are the boundary operators you need to measure to know that the state is pure? And at T1, it's a simple algebra, right? Because you measure a few 2-point functions and they completely characterize the state. Here, it's a complex algebra, and you need to measure e to the minus s. This is what I was saying, right? You need to measure all correlators up to like s point correlators up to accuracy e to the minus s. Here, the naive estimate would be you need to measure all correlators on the boundary up to accuracy e to the minus s prime, where s prime is now the entropy of the Hawking radiation, and s prime is larger than s. So if you think of the formation and evaporation of a small black hole from the perspective of the boundary, you see that it becomes harder and harder to recover the initial state. And that's why I think the page curve is misleading. Now, of course, you can define some algebra that kind of throws away information and gets back information. But this boundary perspective tells you it's a pretty unnatural algebra. And unlike in flat space, you can't just throw out the Hamiltonian, because you throw out the Hamiltonian, it reappears in OPEs and ADS. So, it kind of tells you that, the natural observables is you would keep track of these guys to accuracy e to the minus s, some boundary observables, and they would see the information at all times. And in fact, it gets harder to see the information at later times. So this would be what I would say. Yeah.
Can we consider this in the case where the black hole has entropy 10,000 qubits and n for the ADS? So the ratio of the ADS scale to the Planck scale is like a googolplex. So in that case, I think it would be the case.
You need to form a black hole, right? So you need to form a black hole at least.
Yeah. So I'm saying we throw stuff in, Planckian energy densities, we throw them in, we form a black hole that's like 1,000 qubits, and then they come back out.
You could do that. Now in this case where you form this black hole, which was 1,000 qubits, there's sure, you could do that.
So then I think the claim of islands is that so I think all the things you said before, then Islands would not disagree with. But I think in the case that I've just said, then the claim of Islands would standard island calculations would be that the complexity of recovering it from the boundary at time t3 would be significantly simpler than at t2. Just because the n is a googolplex, whereas the entropy of the black hole is like 1,000. I think that follows
I can see
basically
how you can decouple these factors, because the gravitational effects are always proportional to g to the d minus 2, which is 1 over s. You know, the energy of the Hawking radiation that you have. I'm not sure what you want to do with those parameters.
Yeah, it's possible.
I mean, this is the whole point about black holes, right?
Let's stick a load of energy. Let's stick a load of other energy in the ADS system. So we're forming some black hole, but then we have a load of crap, a much lower temperature, but like including some stuff far out near the ADS scale. So the energy of the ADS system is also really big.
Yeah, but then aren't you just bottlenecked by all that crap?
Sorry, go ahead.
Well, I was thinking of
aren't you just bottlenecked by decoding all that crap even when the black hole evaporates and then just adds to that?
Not if the photons the super high energy photons just go through that crap and make it out to very near the boundary.
Yeah, I mean, maybe you could do something like this. This would be interesting, right?
I'm spitballing here, but I think
but
you could have a setup with them.
Exactly. So you see, it becomes it's very hard to come up with. I mean, maybe you could do this. I don't. You could think of.
Okay, but maybe let's just go back here because I feel like this. Yeah, sorry, go on.
Yeah, it points out how hard it is to make this distinction between what you need to see the page curve and what you need to see the information at all times. You see, so maybe you do something like this.
We've already discussed 6 or 7 circumstances where you should see the page curve.
Okay, but
and then you want to go to one where you find it hard to see.
But
you want me to say how I would
back
to
the distinction
I can do
here.
so.
No, it's the same
so
thing.
Operationally,
go on, please. Ask
but operationally, it seems that like
I can define a swap operator, swapping a boundary operator that has the effect of swapping some radiation modes between the two systems. That's perfectly easy to do with like HKLL for this small black hole. I can define that unitary operator, and then I can define an entropy by that defines trace of rho to the n, and then I analytically continue, that gives entanglement entropy. Or I could do HKLL reconstructions that would let me do state tomography on some photons coming out, some electric fields in some region. I could do that very far from the black hole, and again, I would see a page curve.
How do you see? Sorry, I didn't understand. You'd see a page curve in this setup?
Well, no. So I think that like it's not so
computation that would give a page curve is to define an HKLL reconstruction style swap operator that swaps some photons coming out near the boundary between 2 copies of the system.
And is it a page curve as a function of time or as a function of number of operators?
No, it's a function of the amount of radiation.
Well,
the page curve is always a function of the amount of radiation. It has only ever been a function of amount of radiation. It has nothing to do with time.
I agree with that.
I've never heard anyone other than you, Suvrat, say it has to do with time.
I don't think this is true.
That, like very hand-wavily when we say there's more radiation as a function of time, so we drop time.
I don't think this is true as a sociological statement that no one thinks of the page curve as being a function of time. That I think we
like the amount of radiation and time are linearly monotonic.
No, I think in this case, we see that it's very hard to define the page curve as a function of time. Just to be clear for listeners, just to emphasize what Geoff said. You know, you could look at a function not as a function of time, but as a function of number of insertions that you put in these correlation functions, right? You could try and define an entropy as a function of how many correlators do you keep track of? So of course, if you keep track of very low point correlators, you see a thermal curve. If you keep track of something in the middle, you see some higher and higher thermal entropy. Once you start keeping track of more and more correlators, you see the entropy go down. And that's of course true. But that's not telling you information is coming out of the black hole. It's just telling you as you make more and more accurate measurements, you start seeing the information being out. But that's true at all times.
Sure, I don't think that characterization is at odds with what Geoff is expressing, but I guess
I was rephrasing what Geoff is saying. Yeah,
exactly. Yeah, sure. So
I think the only thing I would emphasize, Suvrat, is I think you're focused on number of points of the correlation function. I'm focused on which degrees of freedom.
Yeah,
I'm
okay,
saying,
so
let's say we
exactly.
look at something that looks like some photons, looks like we're doing some measurements of some photons in a weakly gravitating region, and we're interested in that entropy. That seems like an interesting question, or that state.
Let's just put it this way. It's like, which is the accessible S, right? I mean, I agree that there's an S in both of these bubbles, but I guess Jeff's point is that the S in the top bubble,
yes.
at least if you give ourselves, sorry, are we all on the same screen? Are we all looking at the top of the triangle?
Yeah.
Great.
Yeah.
So the S in the top bubble, right, in this the fiber optics and all the hardware in the world that we've discussed, that setup, right, is an accessible S, meaning you can just sit, wait, collect, repeat, and then all you need to do is just like get enough that you'll be able to do this with adequate precision. Whereas the issue with well, even though it is true that there's an S in the second bubble, it's just not entirely clear what we would do in terms of like what we can imagine doing to access it.
Take a test mass and look at, you have a big LIGO detector and it would detect for you these metrics.
Yeah, no, I guess I agree that it's just that
it would
it'd just be a
huge
little bit more
LIGO
complicated.
detector.
So are we in agreement with that being the
Because,
situation?
you see, the issue now we're getting into is what is more complicated, right? So this.
No, I agree.
Yeah. Lower picture.
I don't even care. I'm happy with both things. I just think they're different questions and they're both interesting questions. And one's the page curve and one's not. One's like some other thing.
I agree with this, and I agree with this, and so I don't think there's any disagreement with this. You can ask both questions, and you see a page curve in one case, and you don't see a page curve in the other, and that's yeah, sure, I agree. There's nothing.
But I do think it's important that when you're talking about fundamental limitations of precision, certainly in quantum gravity and flat space, then the relevant thing is what precision you can get in what size. If you have a large enough region, you should be able to do things to any finite precision in flat space with no cosmological constant or anything, just by doing it on big enough scale. So for example, once you have your photons in a fiber optic cable, you can spread those degrees of freedom out in some huge quantum computer. And then once you've got that set up, once you have that state, there was limited precision in getting to that point. But then after that point, you can do stuff to, arbitrarily high precision.
And
so
conversely,
that's why
Geoff,
it's definitely a meaningful question.
Yeah, and conversely, you agree that if you had like an arbitrarily precise thing in flat space, LIGO, whatever thing, you'd be able to play the game with the gravitational degrees of freedom.
I just want to say,
it's like not obvious to me, but at the very least, there's a well-defined algebra at infinity that you can ask questions about, and I'm happy to do so. And yeah,
let me just correct that slightly, Vasu. Actually,
it's
not arbitrarily precise. Maybe if you go down to the case where we mentioned, it is in terms of the set of observables that we are looking at. If I think in terms of these correlators, which maybe is not what Geoff wants to think of, but I think are the natural set of observables, which are these boundary correlators, it's the same accuracy. It's not that you need much more accuracy to see the information at all times.
Yes, I agree. In terms of number of points, a number of points in the correlator, I think we're in complete agreement. I just think that
the only thing is I'm not trying to distinguish between insertions of the metric and insertions of something else. I'm not throughout. I'm just treating all boundary variables on the same footing, and I'm willing to say if some variable is much harder to measure and that it's much smaller, then I'll throw it out. But it so happens that the metric is as large as these other correlators. So if you just keep track of
but I mean I'm talking about in terms of like devices we have. Okay.
Yeah.
This is slightly different question.
I find that misleading. Let me just say one thing about that. We can go ahead with that, and I think it's fine to ask that question. I just think that our everyday intuition about devices we have needs to be really problematized, because the devices we have are not the devices we could use for really recovering what's written on a piece of paper if you burn it, right? So these fiber optic cables, if you burn a piece of paper, would be able to recover what was written on the piece of paper, right? Those are not the devices we have. So we might need to think much more carefully about what devices we have, right? How you'd set up this device.
I suppose that could be the conversation for another time, because we are running a little bit. This is fun, at least for me. I mean, I don't know about you guys. I thought this was fun.
I had fun.
And well, I mean, there's certainly more to be said. I was hoping that we could at some point set bounties on what sort of problems we'd like to solve. What are the interesting questions aside from the questions we think we've already addressed versus what are the questions we'd want to address. But I guess that'll have to be for another time. I do want to thank you both for doing this. it's pretty cool. So yeah, I mean, if you have any closing thoughts, yeah.
Yeah, I guess I'd like to thank you for hosting, Vasu. It was a lot of fun. I guess it got slightly heated at times, but I think Suvrat and I both had fun. I think, yeah, I guess my thoughts would be that I think these sort of discussions happen a lot. I've had these sort of discussions with Suvrat before. I think when you're not in, a top physics department or somewhere and you're not hearing these discussions, I think democratizing them by putting this sort of thing on YouTube and just seeing stuff, hashing stuff out. And I expect there are things both Suvrat and I said that at some point that were wrong in there, and that's also part of live physics discussions and so on. I think, if you're an undergrad or whatever watching this, then this is what doing quantum gravity research is like. None of us really know what the rules of the game are. We're all sort of making it up, but we're trying to hash stuff out as best we can. So yeah.
Thank you. Thank you very much, Vasu. And I agree completely with what Geoff said. So thank you very much for doing this. I hope it'll be very useful for a lot of people. I know it'll be useful. So thank you. Thank you, Geoff. Thanks. And it was indeed fun. And yeah, I hope we can do this again at some point. Thanks.
Yeah, so hopefully there will be more of this this from this channel. And yeah, I'll see you all next